So this is what's called spectral analysis of numerical errors. So let's start by recalling some of the things we did a couple of classes ago. And we did the von Neumann analysis, and we introduced, to do the von Neumann analysis, we introduced a Fourier decomposition of the solution. So introduce, it was a discrete, finite space, finite, domain, Fourier decomposition of the solution, and it looked like this. We said u at time n at point I, we express it as a sum of Fourier modes in the domain, so j, the discretized domain, j going from minus n to n, and we have here the amplitude, which absorbs all the time dependence, and our mode here, where this capital I is the imaginary square root of minus 1. We use capital I so that we're not confused with our indices, I and j, and we have kj and xi. So here we're summing over all the modes. K indicates all the modes, and xi is the position on the mesh. So xi is equal to I times delta x. So a single harmonic is a particular choice of that value k, and so it is u and I. So let's write k here to indicate that's a particular choice of k, and it has an amplitude Vn and E I k, and let me write now I delta x. And so with this we defined an amplification factor. This amplification factor was G equal to Vn plus 1 over Vn, and we said this is a function of the scheme parameters, and also of the phase angle phi, but not a function of n, our time level. So this should be equal to Vn over Vn minus 1, and so on. And so we were able to express then with this the von Neumann stability criterion in terms of this amplification factor, which is a condition on G that says that the modes must not grow, so G has to be less than equal to 1 for all phase angles, where the phase angle is equal to kj times delta x. So the amplitude of any harmonic may not grow indefinitely in time is what our von Neumann stability condition implies. So now we want to go a little further and have some additional information on the errors. We wish to know more about the time dependence of the amplitude, for example. The amplitude Vn. Remember, our amplification factor does not depend on time, so we know nothing about the time dependence. With just, if we're only using G, we know stability, but we know nothing about the time dependence. We want to know a little bit more about that. So we're going to use, similar to the von Neumann analysis, we're going to use this Fourier decomposition, both on the analytical solution and the numerical solution, and we're going to develop that a little bit more. So we consider now the analytical solution of the convection equation, and represent the analytical solution by a Fourier decomposition in space which we write. Now this is the analytical solution, so recall the analytical solution, we use this wiggle to indicate analytical solution, and so we're going to use the wiggle here. You wiggle Ni, the analytical solution at that point in space and time, is equal to some amplitude B hat E I. We know the analytical solution. It is K, it is the same as the initial condition, but just shifted in time by Ct, where T is the n level on time and the location is xi. So this of course amplitude depends on the initial condition. I'll write it in a moment how it depends on the initial condition, but we can rewrite this with a relation between the speed and a angular velocity. I'm going to put the wiggle indicating that it's the analytical, the exact one, divided by k. Okay, and so now we can write then this as u wiggle Ni equal to v hat. And I'm going to separate these two terms into exponentials. I can separate that. So I kxi and exponential of minus, it's got a minus there, I, my imaginary number, and now I put the k is absorbed in here because we have this relation here, and so we write omega wiggle, the exact pulsation speed, and Tn. So a single harmonic is, so again, like we did before, similar to the von Neumann analysis, we specify just one value of k, and we write v of k and e ik, we write xi as I delta x, and e minus I, and we write the omega, and the time as n delta t. I'm going to make reference to this guy in a little moment, so I'm going to call it star. And here, this amplitude is obtained from the Fourier decomposition of the initial condition. So let's consider the initial condition to be, let's call it u at time 0 equal to just u0 of x. And so with that, v hat k is equal to, remember we're looking at a finite domain between minus L and L. We assume periodicity of our solution for this analysis, and we continue to do so. This is the initial condition, e to the minus I kx dx. So this is our Fourier decomposition of the initial condition, which is used to obtain those amplitudes over here. So we are going to assume that the initial condition is represented exactly on the mesh. Okay, so that for the numerical amplitude, we can continue to use this v hat. So assume that the initial condition is represented exactly on the mesh. Except for, of course, just round of errors. Machine errors are okay, but we consider that to be exactly. So we can now write a numerical amplitude similar to star. This one was the analytical one. So now we write the numerical amplitude represented similarly to star. And so I'm going to write for the numerical amplitude, Vn is equal to this V hat from the initial condition and e to the minus I omega and delta t. So this is the numerical angular velocity. Minus I omega delta t and to the power n is the same thing, right? So basically that we noticed here that we're changing. Now notice here that we're changing this to be the numerical one. Okay. Now, if you recall from physics of plane waves that for plane waves, this expression, omega as a function of k, is called a dispersion relation. You might recall this. So now let's write with the amplification factor. Recall that Vn is equal to the amplification factor G times Vn minus 1. And then Vn minus 1, I also can use the amplification factor to write it. So we could again have a G, another G, so G squared times Vn minus 2. And since it doesn't depend on time, I can do it for all time steps and so on until G to the power n times V0. But V0 is the initial condition, so this is G to the power n times V hat k, our initial condition. Right? So you see that if I compare these two, if I compare this, this is Vn, so they're the same. I compare these two, you see that V hat k appears on both. So this happens to be G. It's the same. It's right here. Okay? So, well, I'll write it in the next slide. G is equal to e to the minus I omega delta t. And this defines our numerical omega, basically, which was kind of introduced here without knowing what it was. okay, the numerical omega. So we have that G is equal to e to the minus I omega delta t, and this defines our numerical omega of k. Similarly, we can do the same, but using the analytical solution. And so V wiggle n is equal to e minus I omega wiggle, the exact one, delta t to the power n times this V hat, the initial condition. And we use this now to define a exact amplification factor. So this will allow us to study the frequency spectrum of the numerical errors. But now note that omega is a complex function. So G is equal to the modulus of G times e to the minus I phi, where phi is some phase angle. Okay, and of course Vn, which is equal to G Vn minus 1, is equal to this amplitude of G times e minus I phi Vn minus 1. So now, the error in amplitude is error d equal to G over G exact. And this represents the diffusion or dissipation error. And the error in the phase of the solution is E phi equal to the numerical one divided by the, here's a wiggle that is going to be, I hope you see it, there. And this is called dispersion error. This is the usual definition for convection-dominated flows. As an aside, this is the usual definition for convection-dominated flows. But if you have pure diffusion, then for pure diffusion problems, for pure parabolic problems, then you would have that, in that case, the phase angle is 0 for the parabolic one, and so you can divide by 0, and so use the alternative definition error phi equal to phi numerical minus phi exact, so that you don't have a problem divided by 0 there. For the convection equation, of course, for the convection, phi exact is equal to Kc delta delta t. C delta t is our how much the solution is moving in each time step. The exact analytical solution should move at that rate. So now we have two definitions of errors, the diffusion error and the dispersion error. And what we're going to look at, you see that these depend on our Fourier decomposition of the solution like we did in the von Neumann analysis. Before we used that just to get our amplification factor G, but now we could use it to get these errors and look at how those errors turn out for each of our numerical schemes. So that's what we do next.